Good morning. Today we're going to discuss about the ideal gas equation, and we'll talk about ideal gases and real gases to sort of understand under what conditions do gases behave like an ideal gas and when they do not. So this is a part of chapter 3, which we have been dealing for the past few weeks. This is the last part of chapter 3, where we will be talking about the ideal gas equation and also the non-ideal gas model and see how we can make use of them under what conditions. So first, when we talk about ideal gas, it is simply an equation of state. Okay, equation of state simply says that it's an equation that relates pressure, temperature, and specific volume of a substance. So if you have any equation that can relate pressure, volume, and temperature of any given substance, we call that as an equation of state. So ideal gas equation that we have seen before several times as part of different courses is simply another equation of state which relates pressure, volume, and temperature for gases under a specially selected region or a properly selected region. Okay, so here we're not saying of an ideal gas. We're saying generally it can predict the PVT behavior of any given gas within some properly selected region. Now, within that properly selected region, the relationship between pressure, volume, and temperature is given by this equation, which is also known as the ideal gas equation of state, right? And this is essentially true. This equation, which relates pressure, volume, and temperature, is essentially true for gases which behave like an ideal gas. Okay, we'll talk about what is an ideal gas, what is a real gas in a bit. Now let's look at this equation. So this equation relates the pressure in kilopascal to the specific volume in meter cube per kilogram to the temperature, which is in given Kelvin. And it is related with this constant, which is called the gas constant. All right, the gas constant R has units of kilojoule per kilogram Kelvin, and it is related to the universal gas constant, which is has a fixed value of 8.314 kilojoule per kilomole Kelvin through this equation where the gas constant for any given gas is equal to the universal gas constant divided by the molar mass for that gas. So let's say if you want to find out the gas constant for air, it'll be equal to the universal gas constant, which has a fixed value of 8.314 kilojoule per kilomole Kelvin, divided by the molar mass for air. Okay, so this is how it works. Now, M again being the molar mass or the molecular weight of any given substance. The molecular weight for all known substances or all relevant substances are given in table A1 of your book. So please refer to that. And the molar mass or the molecular weight in simple terms is simply the mass of 1 mole of a substance in grams, or basically the mass of 1 kilomole of a substance in kilograms. In other words, it is simply equal to the molecular weight of a substance, and you can either calculate it by adding up the mass of different elements within a given compound, or you could simply refer to table A1. Okay. Now, ideal gas equation of state also has several other forms. One of being this one where we are relating pressure times volume to the number of moles N and the universal gas constant times the temperature. So in all of these equations, pressure is always in kilopascal and temperature is always in Kelvin. The other elements, the other part of this equation, they can have different units depending on what it is, right? So here we are having volume. So volume will be in meter cube. Number of moles is simply a number. RU is universal gas constant, talking about kilojoule per kilomole Kelvin. So number of moles isn't typically telling you the number in terms of how many moles or how many kilomoles do you have. We can also write it in this format where what happens is that we are having the same thing, pressure times volume, but it is equal to the mass of the substance times the gas constant times the temperature. So if you compare these two equations, the main difference is that instead of number of moles, we are having mass. And because we are having mass, we are making use of the gas constant instead of the universal gas constant. So the main difference is right there. Okay. Now, again, there's the relationship between the number of moles and the mass of a substance at any given condition. And it is given by this formula where the mass is equal to the molar mass times the number of moles. Okay, so this being the molar mass, which you can get from table A1 for any given any substance of interest. Now, there are, of course, other formats or other forms of the equation. The PV is equal to MRT. Well, you could send the mass here to and divide it by the volume. So it becomes pressure times volume to become pressure times volume by mass is equal to RT, or volume by mass is nothing but the specific volume. And this becomes PV is equal to RT, which is the equation that we have seen before. You could also write it as pressure is equal to density times RT, but that's not something we use very frequently. Now, when you're dealing with an ideal gas with a fixed mass, let's say like in a closed system, which is undergoing any given change of state, it's still being an ideal gas. It has to satisfy the ideal gas equation at all states, which means that we could write P1 V1 by T1 is equal to P2 V2 by T2, as long as the gas is ideal and as long as the system is closed or system has a fixed mass, we can make use of this equation. Okay, so this is these are the different forms of the ideal gas equation that will be useful when we are solving problems related to ideal gas behavior and different systems. Now, it's important to remember that we said ideal gas equation of state applies in a specially selected region. It is not applicable everywhere, and the ideal gas relation is not applicable to real gases. All right, so we have to talk about what are real gases, right? And basically, the idea is to say that you cannot use ideal gas equation anywhere and everywhere to relate pressure, volume, and temperature for gases. Gases in some special conditions behave like an ideal gas. In some other conditions, they don't behave like an ideal gas, and they behave like what are called as real gases. Okay. In other words, you could say real gases, they behave like an ideal gas at specific conditions, which are basically at low densities. Low densities can mean low pressure or high temperature, because these are the conditions at which the molecules are far away, and then the assumptions that are being used for coming up with the ideal gas equation, they become true. So basically, ideal gas equation represents real gases as long as they are at low densities. Okay. Now we will talk a little bit more about what is defined as a low density, right? Because low density for one may not be a low density for the other. So this is a very relative matter. So the question is, how do you what is the criteria, or how do you define what is a low pressure and high temperature? Or in other words, how do you define low density? Well, whenever we talk about low pressure or high pressure, or high temperature or low temperature, it is all with respect to critical temperature or pressure. Critical temperature is Tc, critical pressure is Pc. This is something that we have been dealing with, and we know that critical temperature and pressure are the points where the saturated liquid and vapor lines meet. This is something we did in the first part of chapter 2. So when you're looking at saturated liquid line, saturated vapor line, the point where they meet, that is the critical point. So that the temperature there is Tc, the pressure there is at that point is Pc. Okay. Now, basically the idea is that when you're at a condition where the pressure is low with respect to Pc, so P should be smaller than Pc, and the temperature is greater than Tc, or simply temperature simply greater, does not have to be much greater. When the pressure is smaller than critical pressure, temperature is greater than Tc, then the gas will behave like an ideal gas. So essentially, if you're near the critical region, you're going to see non-ideal gas behavior. But as you move away from the critical region, especially towards the right where the temperature is high or the pressure is low or both, that's when we're going to see gases behaving like an ideal gas, simply because under those conditions, the gases are at low densities, molecules are far away, they don't interact with each other, and those are the assumptions used for coming up with the ideal gas equation of state, which is PV is equal to RT. Okay, so this is applicable under those conditions. It's applicable here for any given gas that we are dealing with. Now, what do we do when we are not under those conditions, right? There may be situations where you are at a high density region, or you are at a region where it's just close to the critical point. What do you do under such cases? Well, we have a way to handle that, and the way we handle such situations is through the use of a factor called compressibility factor Z. Now, compressibility factor Z is simply a factor which accounts for the deviation of real gases from ideal gas behavior at a fixed temperature and pressure. So if you tell me what is the temperature and pressure, I can tell you how far are the gases going to be in terms of their behavior at that temperature and pressure as compared to an ideal gas behavior. Now, if gases behave like an ideal gas, well, PV would be equal to RT. When gases do not behave like an ideal gas, then for real gases, PV does not have to be equal to RT. Okay, so what we do is we come up with this compressibility factor Z, which is simply relating pressure and volume to RT through the factor Z. And the idea is that we write PV is ZRT. If Z is equal to 1, then PV is equal to RT. It's an ideal gas. If Z is more than 1 or less than 1, well, it's not an ideal gas, right? So the factor Z, which is the compressibility factor, it gives us an indication of how far a gas is from ideal gas behavior. Okay, so therefore Z as shown here is defined as pressure times volume by RT. Now, the more Z is away, the more compressibility factor is away from unity, the more the gas will deviate from ideal gas behavior. Okay, and we simply have to make use of this PV is equal to ZRT relation to determine the relationship between pressure, volume, and temperature for that gas under those conditions. That's what it is. There's nothing complicated in here. Okay, now when we're looking at Z, we can also calculate it as specific volume actual divided by specific volume ideal. Now, what does it mean? Specific volume ideal means the specific volume that we can calculate from ideal gas equation. Okay. And specific volume actual could be the specific volume that we actually measure it, right? So Z is a quantity that we can simply go ahead and measure. And so the compressibility factor is a very good way sort of to understand what really is happening in terms of the behavior of the gases and how close or how far they are from the ideal gas behavior. So you should remember both ways of defining Z, they are equivalent, okay, and they will basically be useful as used for calculating the pressure volume relations, pressure volume temperature relationship at all conditions. So in general, you could simply say PV is equal to ZRT. And when the gas is ideal, Z becomes 1 and PV becomes equal to RT. Okay, but Z can be greater than 1, Z can be smaller than 1. It just depends on the conditions that we are talking about. So the question is then, how do we find Z? Because Z is a very important factor, and we said it's something that's going to help us understand the gas behavior, especially when it's not under ideal conditions. Well, you can simply do an experiment at different pressures and temperatures and calculate Z as experimentally measured pressure, volume by temperature, well, by RT, right? So this is something that will give you Z directly, because Z we said is equal to pressure times volume by RT. Okay, so if you have a given pressure and temperature, the gas constant is anyway fixed. If you just measure the specific volume at that condition, at that pressure and temperature, you're calculating Z directly. You just have to keep repeating it for different temperatures and you have Z. Now we can plot Z as a function of pressure for different temperatures, 35 Kelvin, 50, 16, so on. And this is done for hydrogen. And what we will see is a plot showing how the value for Z changes at different conditions, right? And we can see that as we go to very low pressures and relatively high temperatures, from 35 to 300, we can see that things start to approach Z is equal to 1. So low temperature is very far from 1, okay, but high temperature like this, it is kind of close to 1. But again, high temperature, if you want to be close to 1, high temperature is sometimes may not be enough. You have to go to lower pressure. So lower pressure, no matter at what temperature, if you go to lower pressure, everything approaches 1. Okay, so this is how it looks like. But the problem here is that this is done for hydrogen, okay, and we will have to come up with a different chart for every gas, and that makes things very, very complicated. Well, luckily there's a solution for it. Instead of plotting the chart in terms of pressure and temperature, if you do the plot, same plot again, but in terms of reduced temperature and reduced pressure, then everything lines up. What is reduced temperature and reduced pressure mean? Well, reduced temperature simply means instead of plotting with respect to temperature, we plot at reduced temperature, which is defined as temperature by critical temperature. Okay, and reduced pressure, which is defined as pressure by critical pressure. Because you remember we said when we say high or low pressure, it is with respect to critical pressure and critical temperature. So if you do the same plot for Z, but with respect to reduced pressure being equal to P by PC. And if you plot it at different reduced temperatures being temperature by T critical for different gases, what we'll see is that for all the gases, everything lines up. So this one chart represents for methane, ethylene, ethane, propane, isopentane, nitrogen, CO2, water, and everything, right? And you can see all of these were measured at different conditions. The experimental data is shown here. This is for methane, and you have ethylene here and nitrogen somewhere here. And so the water is here in these solid circles. So the basic idea is that as long as you're plotting in pressure, in terms of reduced temperature and pressure, the plot lines up. One chart works for all gases. Okay, as long as the chart is drawn with respect to reduced temperature and reduced pressure. So that's the brilliant thing, and this is extremely useful for us. So again, here also the same thing works out when we're looking at reduced temperature of 1. Okay, TR is equal to 1. If you keep going to lower pressures, which is lower reduced pressure as well, the compressibility factor approaches 1. As we go higher from TR is equal to 1 to higher and higher temperatures, you can see that the compressibility factor Z already starts approaching 1 or starts going close to 1. And at TR is equal to 2, it is almost 1. It's very close to 1, right? It's between 0.98 to 0.1. And this is again to say that when we are at a high temperature with respect to T critical, low pressure with respect to P critical, we will be approaching Z is equal to 1, which is the ideal gas condition. Okay, and T by T, T greater than TC basically refers to T by TC greater than 1 or TR greater than 1. As you go higher and higher, we approach ideal gas equation of state, or conditions at which the gases behave like an ideal gas. So this is about the compressibility factor. We will look at this chart, which is there in your in the property tables and charts at the end of the book. We will make use of this and solve a couple of problems, and that's something that we will do tomorrow. Have a great day. See you tomorrow.